So in this video, I want to talk about multiplying vectors. And, well, I guess it would be a lie if I was going to say that this video I'm just going to talk about multiplying vectors, because multiplying vectors is actually a lot more complicated than it seems. And it's shocking because, we think, okay, well, we can add two vectors and we get a vector. We can subtract two vectors and we get a vector. And so you might think, well, when we multiply two vectors, we get a vector. That's not actually the whole story. When we multiply two vectors, we can either get a vector. So I'm just going to put in quotes multiply. When we multiply two vectors, we can get a vector or we can get a scalar. And it depends on how we multiply the vectors. There's actually two different ways that we can multiply vectors. So in the next couple of videos, I'm going to talk about multiplying vectors using something called the dot product. And that's what it is when you multiply two vectors and you get a scalar. The type of multiplication you're doing is called the dot product. And if you multiply two vectors and you get a vector, it's called the cross product. And we'll talk about the cross product a couple videos down the road after I thoroughly talk about the dot product. There's a lot to say about the dot product. There's also a lot to say about the cross product. But I want to spend a couple videos talking about the dot product first, and then after a couple of videos, after I feel that I've covered all the concepts I feel like I need for the dot product, we'll move on to talking about the cross product. Let's start by talking about what the dot product is, though. So what is the dot product? Well, let's say that I have two vectors, okay? So I've got some vector u, and it's got components, and again, I'm going to list as if this was a three-dimensional vector. Of course, this would work in 2 dimensions as well, but since we live in 3 dimensions in multivariable calculus, I'm going to live in 3 dimensions. So I have a vector u that has components a1, a2, and a3, and I have a vector v that has components b1, b2, and b3. The dot product of u with v, and the way you write that down is if I want to say I want the dot product, I write u, and I put a little dot here. Now you might be thinking, oh, I'm used to doing this in multiplication. As opposed to multiplication, because in multiplication with normal numbers, this is the same as this, which is the same as this. There's multiple different ways to represent the same multiplication. But in this case, in vector multiplication, this symbol actually has meaning behind it, and you actually need to write down the right symbol, because if you write down something like this, this means something completely different than this. So that dot that I wrote down there, that is really important and powerful. So the dot product is u with a little dot, as you would suspect, with v. And what that's equal to, the way you would compute the dot product is it's equal to you multiply like components and add them together. So by multiplying like components, you are going to multiply the first 2 components and add it to the second 2 components and add it to the third 2 components. Again, all of them multiplied together. So what the dot product looks like is it looks like a1 times b1 plus a2 times b2 plus a3 times b3. And this is what this is the formula for the dot product. So, if you wanted to put this into words, another way you could say this is multiply like components and add the products. This is the way to get the dot product. So if I had a vector with 2 dimensions, or if I had 2 vectors, then the dot product would be a1, b1 plus a2, b2. So let's do a couple of examples of computing some dot products. So let's say for an example, let's say I have the vector u is equal to, and we'll start in 2 dimensions, then we'll do 3 dimensions. So let's say I've got u as the vector 3, 5, and v, and I guess I should actually color code this. So let me do that really quickly. Let's make this the blue vector. And we have another vector v, which is equal to the vector let's say it's the vector 6, 2. So the dot product, so U dotted, and I don't like that hat, U dotted with V is going to be equal to the first two components multiplied together, or the each first component multiplied together. So we're going to take the 3 and multiply it by the 6. And we're going to add it to the 5 multiplied by the 2. Multiply the first components together, multiply the second components together. And if I do that, I get 18 plus 10, and so I get that the dot product of U and V is 28. To do another example in 3 dimensions, let's say I have a vector U and it's equal to the vector 1, 3, 6, and I have the vector V, which is equal to 1/2, 3, and 1/4 to get, and pi, maybe to get some fractions, to get some weird numbers in here just to practice. And again, this is going to be more beneficial if you can pause the video and try this on your own. I think learning is much more beneficial if you can stop and try and compute some dot products on your own and work ahead of me. And if you get stuck, then obviously unpause the video and see what I'm doing. But if you can do it ahead of me, then I think you're going to understand the content a lot better. So U dotted with V, when it looks like this, what we're going to get is we're going to get a 1 times a 1/2, the first components multiplied together, plus the second components multiplied together. So we have a 3 times a 3. So 3 times 3, plus the final two components multiplied together, which is going to be 6 times pi. So the result of that is going to be, well, 1 times a half is a half. A half plus 9, that's 9.5. So that would be, let's see, that would be, well, I think that would be 19 over 2. So that would be 19 over 2 plus 6 pi. That is the dot product of U and V. And I guess to have one final example, let's say, just so that we can get practice with notation, let's say that U is equal to I hat minus 2 times J hat plus 3 times K hat. And V is equal to negative 3 I hat plus 6J hat minus K hat. Well, then U dotted with V, U dotted with V is going to equal, well, we have to, what do these vectors really look like? I mean, we can see that they're in their I, J, and K components, but what do these vectors really look like? Well, in our brains, we can remember that this vector looks like 1 times I hat. Remember, I hat just looks like the vector 1, 0, 0. So 1, if we have just I hat by itself, 1 times I hat, well, that's just all of this. And we're going to add it to, we're actually going to subtract from it 2 times J hat, which is going to equal negative 2, 0, 0. And then add to it 3 times K hat, which is going to equal 0, 0, 3. And I think you can see that the vector we create is 1, negative 2, 3. Likewise, with V, we can see that really V looks like the vector negative 3, 6, negative 1, which makes the dot product a lot easier to compute. When we look at it using these methods up here, well, we can clearly see that we multiply the first components together, which is the 1 and the negative 3. We get it to multiplying the second components together, which is the negative 2 and the 6. That negative 2 was a little sloppy. Let me fix that. The negative 2 and the 6, and then we add it to, we add it to the negative 3. Oops, that's in blue, and it's a positive 3, not a negative 3. The 3 and the negative 1. And what does that get computationally? Well, what that results in computationally is negative 3 minus 12 minus 3. That's a negative 6 minus 12. That results in a negative 18 dot product. So, got some practice with recognizing the different forms of writing a vector, and we got some practice computing the dot product. What I'm going to do in the next video is talk about some observations about what the dot product actually represents in some applications. I'm leaving out a little bit of how to do things computationally because I think it would make more sense to talk about them in light of the applications. So I'll see you guys in the next video.